Chapter 15, number 43. A solid block is attached to a spring scale. When the block is suspended in air, the scale reads 21.2 newtons. When it is completely immersed in water, the scale reads 18.2 newtons. What are A, the volume, and B, the density of the block? So what we're going to do here is we're going to want to look at the buoyant force, which will give us the volume eventually, and that means we're going to have to do some free body diagrams. So let's do those for the two situations. So in case one, we just have the spring force balancing out the weight. In the second case, we have a different spring force, Fs star, and it's balancing out the weight, but there's also a buoyant force holding up the block. So if we apply Newton's first law, or Newton's second law, to the first situation, the sum of the forces from the diagram is Fs minus Fg, and we know that the sum of the forces is, from Newton's second law, 0. So the scale reads the weight of the block. So that might be useful. And then in the second case, we have the sum of the forces is the scale in its new reading minus the weight minus the buoyant force. And the second law tells us that that has to be 0 because there's no acceleration going on. We see immediately the convenience that came from having this in both. So we can now start putting stuff together, and we can start saying that the scale force minus the scale in the first case minus the buoyant force is 0. So the buoyant force is the original reading on the scale minus the reading once it's submerged, which in this case is 21.2 newtons minus 18.2 newtons, or 3 newtons of buoyant force. But we also know that the buoyant force is the density of the water times the volume times g. So the volume must be the buoyant force over the density of water times g. So 3 newtons over, we assume it's clear water, it's still water because they don't say anything otherwise, so we'll take a density of 1,000 kilograms per meter cubed, and then we have 9.8 meters per second squared, and so the volume turns out to be 3.058 times 10 to the minus 4 meters cubed, and given that we have 3 sig figs, it's really 3.06 times 10 to the minus 4 cubic meters. So that was part A. Part B wants the density of the block. That's pretty easy though, because the density of the block is the mass of the block over the volume, and the mass of the block is going to be its weight over g per volume, because Fg is just m times g. So we get something like Fg over gv. Fg was 2.12 newtons because we had shown earlier that the scale read the weight when it wasn't being suspended in water. And then we have 9.81 meters per second square times 3.06 times 10 to the minus 4 meters cubed, which is 7062.3 kilogram per meter cubed. To the correct number of sig figs, I guess I should say it's 760 kilograms per meter cubed.